Dear students, I welcome you in this lecture on projections on Hilbert spaces. In this lecture, we are going to define projections on Hilbert spaces and study their properties. Before that, let us see a simple property of projection. P is projection on closed linear subspace M of H if and only if I minus P is projection on M perpendicular. So P is projection on M if and only if I minus P is projection on M perpendicular. It is fairly simple to prove this property. In fact, it is obvious. Still, I have supplied you the proof in notes. You may go through this. Remember the statement that P is projection on M if and only if I minus P is projection on M perpendicular. Now, let us define projection on Hilbert space. A function P from H to H is called projection if it satisfies four properties. First property, that P is linear. Second property, P is continuous or bounded. Continuous means bounded. The third property, it is idempotent. That is, P composition P or P square is equal to P. And fourth property, P is self-adjoint. We have seen in the last theorem that P is self-adjoint is equivalent to the statement M is orthogonal to N, where M is range of P and N is kernel of P. So due to this it is called a perpendicular projection, and we are going to study only perpendicular projections. So throughout this section, projection will always mean a perpendicular projection. So projection is nothing but a perpendicular projection. Okay. So projection satisfies these four properties: linearity, continuity, and P composition P equals to P. Further, it is self-adjoint, that is, range and kernel are orthogonal to each other. Let us see an example. In this example, we will prove some basic properties of projections. So here we have these three properties. P is projection on a closed linear subspace of H. M is closed linear subspace of H, and P is projection on M, that is, range of P is M. Then we have to prove that these three conditions or three statements, Px is equal to X, X belongs to M, and norm of Px is equal to norm of X are equivalent. So Px is equal to X. So first we will prove that 1 implies 2. Hypothesis is Px is equal to X. This implies that P of X plus 0 equals to X, which belongs to M, by definition of projection on M. Then we will prove the implication X belongs to M. If X belongs to M, we could write Px plus 0 equals to X. Since P is projection on M, we have already seen what is range of projection. Range of projection is nothing but set of those vectors which are fixed by P. So if x belongs to M, then we can write Px is equal to x. Hence Px plus 0 equals to x, where x belongs to M and 0 belongs to M perpendicular. So this implies Px is equal to x by definition of P. The proof of second implies third. Let x belongs to M. Again, Px plus 0 equals to x. So this implies Px is equal to x, and if two vectors are equal, then their norms are equal, that is norm of Px equals to norm of x. Finally, we will prove third implies second. Let norm of Px equals to norm of x. We could write x in the form Px plus I minus Px. X we can write as Px plus I minus Px. So by Pythagoras theorem, we can apply Pythagoras theorem because Px belongs to M and I minus Px belongs to M perpendicular. So these two vectors Px and I minus Px, Px and I minus Px are orthogonal to each other. So by Pythagoras theorem, norm of x square equals to norm of Px square plus norm of I minus Px square. This implies that norm of I minus Px must be equal to 0, so that Ix is equal to Px and we have x is equal to Px, or x minus Px is equal to 0. So considering these arguments, we get that Px is equal to x, and hence x belongs to M. Because Px belongs to M, what is M? It is nothing but range of P. So that's why Px clearly belongs to M. So if Px is equal to x implies Px belongs to M. This is what we wish to prove. Let us see another example in which we will study some basic properties of projections. M is a closed linear subspace of H and P is projection on M, that is M is range of P. M is range of P. Okay. Then these properties are true. First, P is positive operator on H. Second property, I minus P is also positive operator on H. Recall that P is projection on M if and only if I minus P is projection on M perpendicular. So by using that result, we immediately get the second property from first once we prove. Third is that 0 is less equal to P is less equal to I. We will interpret this once we prove it. And finally, we have to prove that norm of P is equal to 1. Norm of P is less equal to 1. So let us prove this properties one by one. Consider Z is equal to x plus I by H. Then we could take x in M and y in M perpendicular, because we can write H as direct sum of M and M perpendicular. With this representation, let us calculate what is inner product of Pz and Z. So that equals to inner product of Px plus y and x plus y. Since Py equals to 0, because M perpendicular is null space of P, so this gets simplified to inner product of x and x plus y due to two reasons. First, Px is equal to x, and secondly, Py is equal to 0. So this gives us inner product of x plus xy, but again inner product of x and y is 0. So we get that this is equal to, this gets simplified to inner product of x and x is equal to norm of x square, which is greater equal to 0. So inner product of pz and z is equal to 0. And in this sense, P is called positive operator. Positive operator means inner product of pz and z is non-negative for every z belongs to H. Let us prove another result. Second property. If z is equal to y plus x, then again by taking y in M perpendicular and x in M, which we can write as M perpendicular, we can write inner product of I minus pz and z. After evaluation, as in the previous case, it is nothing but it is actually equals to norm of y square, and that norm of y square is non-negative. So again inner product of I minus p z is greater equal to 0, hence I minus p is positive operator. Next part, since p is positive operator, we have 0 is less equal to p. Also I minus p is positive operator, again we have 0 is less equal to I minus p. So it follows that p is less equal to I. It follows that p is less equal to I. So third property was fairly simple to prove, and if we combine this, we get the desired result that if p is I, and here it is already 0 is less equal to p, and if we combine this, we get the required result that 0 is less equal to p is less equal to I. Now again we'll complete the example by proving fourth property. So for proving the fourth property, take z is equal to x plus y, where x belongs to M and y belongs to M perpendicular. With this, norm of pz equals to norm of px plus y, which is equal to norm of x, and this we could write as norm of ix is equal to norm of x. So we get the required conclusion that norm of p is less equal to norm of iz. So with this we have norm of pz is less equal to norm of z, and if we take supremum, we immediately get that norm of p is less equal to norm of I, which is equal to 1. Okay, so norm of p is less equal to 1. This is what we wish to prove. Thank you.